Hello and welcome to Module 2, Lesson 2. So this is the types of minerals. So if we think about this question, why are diamond and graphite so different? So they're both made out of carbon, but they look drastically different. So graphite you use in your pencil. Diamond is a really expensive gemstone. So the difference is that their chemical bonds, the way that they're formed, are different. So the graphite, for example, is more loosely bound, whereas a diamond is more tightly compact and it's formed by heat and pressure. So that's the main difference. All right, so like I said, chemical bonds make a big difference. So if we look at the chemical bond here, this is carbon dioxide. And so carbon dioxide is one carbon, two oxygens. And so these little things, these little dots here represent the electrons. And so you can see carbon electrons, oxygen electrons. So you can see right here they're sharing. So that's covalent, like we learned before. And so a chemical bond is basically just what holds the atom together. So in this case, in all cases, it's electrons. All right. So when we look at mineral groups, we look at how those things are bonded, and that kind of makes up the mineral group. So what kind of elements are in the minerals, and then also how they're bound together. And so there's one group, which is the main group called silicates. And so silicates contain silicon and oxygen, so hence silicate. The ATE ending actually means with oxygen. So silicate represents silicon, and then ATE represents with oxygen. So silicon and oxygen. So they make up 96% of the Earth's crust. All the minerals in the Earth are made mostly of silicates. So the chances that you looked at silicate in the lab were pretty great. I think all of them, all of them but one were a silicate. And that was what was that? That was the magnetite. It wasn't. Then if we look at the different types of silicates we have, or not different types, but if we look at the silicates, they're bound together by something called a tetrahedron. And so a tetrahedron, let me just move my picture here. A tetrahedron is just this three-dimensional shape. I'll show you in a minute. But it resembles like a pyramid. Looking at this, this is the silica tetrahedron. So you can see the little red balls here are oxygen, and then in the middle is silicon. So this is kind of blown up. This is more what it looks like. They're more tightly packed, but you can see the silicon in the middle and then four oxygens on the outside. So that's what makes up the silicate. So silicon and oxygen bound together in this kind of pyramidal shape. So this forms really nice tight bonds. And they form in different shapes. So there's lots of different ways that they form. And those ways that they form, those represent and they're shown in the way that they break. So like the cleavage and fracture that we looked at in the lab. All right, so the bonds really help determine how, like I said, how it breaks. So if they're really kind of flatly bound together, then they're going to break as cleavage. And then if they're not tightly bound, or they're just kind of together, not really in sheets or anything like that, then they'll be breaking just in chunks as fracture. So like I mentioned, it has one silicon and four oxygens, which makes up the silicate tetrahedron, is often what it's referred to as. So you can see these different ways that it bonds together. So we've got the single tetrahedron, and then we can see there's a couple different ways that it can bond. So three or more directions, or just two. And then from there, it bonds in these four different ways. So we've got examples they give you: asbestos. That is an example of a single chain, double chain, amphibole, which is a mineral, mica, which is a mineral, and then quartz, which is a mineral. They're all minerals. So you guys looked at quartz. We did not look at these three examples at all, but I do have them. This is a good example, like it shows here, is mica. There's two types of mica, and I'll show you those in class. I'll get my minerals out, and you guys can take a look at these different types of minerals. But it breaks off in really thin sheets, and that's why it's called a sheet bonding. And it breaks off into these really thin, tiny, or really thin, kind of transparent sheets. Really weird. It almost looks like plastic and not a mineral. This would be fracture. So the quartz fractures, whereas mica has cleavage. Asbestos is also fracture. Amphibole, that example happens to be fracture as well, but there's other minerals that sometimes with the double chain could result in cleavage. But generally, when it's in sheets is when it causes cleavage. All right, so some other mineral groups besides silicates. So silicates, remember, are 96% of all the mineral groups. So out of the other 4%, we have carbonates. So carbonates, here's the word carbon. So that means with carbon. And then ATE means with oxygen. So carbon and oxygen bound together. And so you can see that here. And then oxides, anything that's combined with oxygen, not carbon, but anything that's combined with oxygen. So that would be something like an oxygen and a metal. So hematite, you guys looked at that in the lab. That was the red rock that you guys looked at. So that was iron and oxygen. And so what happens with the carbonates is that when the magma is really dense, it rises up and cools in different layers and it crystallizes, which is kind of cool. We get to see different minerals crystallizing within the carbonate. And then also oxides, they produce metals. So like I mentioned before, hematite is a really good example. All right, and then sulfides and sulfates. So sulfides, they are just something that's bound with sulfur. So this is an example of pyrite. I showed you that yesterday when we were going over how to do the street test and the mineral test. So pyrite is iron and sulfur. And then sulfate, there's that ATE ending again. So that means with oxygen. So sulfur and oxygen combined together, and it can form a variety of things, but that's just what a sulfate is. So those 4 things that I just mentioned are all just making up 4% of the minerals on Earth. All right, and then we've got a few more. So we've got halides. That would be like our salts. So NaCl, which is a natural form of salt, like halite, for example. Some of you thought that the gypsum and calcite was halite, except for halite tastes salty if you were to taste it. And then the last one, native elements. So native elements would be just like silver by itself, gold by itself, tin by itself. So those are just one element only. So those would be any of our, what we typically refer to as metals from the periodic table. All right, so some minerals have an economic value, meaning that we can mine them for a profit. So they might be considered an ore, or we might use them in batteries or just general things that humans use. So so they are valuable, and we can mine them for money. So those are called ores. And so if we can mine it for a profit, we call it an ore. So gemstones, diamonds, sometimes quarry rock, sometimes granite, for example, like for countertops, we can mine that for a profit. All right, and they're usually found deep in the earth. So usually this involves mining, so digging into the ground, either underground or above ground, but we're removing large chunks of rock to get to the source of mineral that we want. All right, and then gems just happen to be things that we wear. So jewelry, for example, is considered a gemstone. So basically anything that we might use as jewelry is a gem. And lots of minerals can be gems. So diamond, for example, is a gem. Sapphire is a gem. Opal is a gem. So all of these things, emeralds, etc. And that's it.